Okay, good evening everyone. Welcome to One Concept, Multiple Tools and Multiple Learnings. So today the topic here would be about forces, application of Newton's laws of motion, and the method of drawing the free body diagram, or what software tools or what simulation tools are available for us to do all this. Okay, so without wasting your time, let us start with this. So this is what is the first one, which many of us are aware. We have been using this one for a very longer time. Okay, let us begin with this. So there is a trolley here, and there are two ropes which are being kept over here. There are knots being kept over here, which indicates the position of the people. So I can now, if I put one of them over here, for example, which indicates that this man is going to pull the trolley towards the left. So as a result of it, when I click on this go button, so automatically there is a force and the trolley starts moving towards the left over here. Okay, and now if I put more number of people over here, that is why I put one more here, then the force is much higher, so it keeps on moving automatically to a larger extent. Now if on the other hand, if suppose if I take one more person and put it over here, then there's a right force acting over here. So there's a possibility it can move, but unfortunately, since the left force is larger than the right force, the object will not move. So these kinds of things can be told. And if you want, you can put the values of these forces also. You can say each value is equal to 50 Newton. So this is 50, this is 100, 150 here, 50 here. The net force is more along the left-hand side. So you can say that the trolley is in this direction, right? And you can also give some of the forces, which says the net force acting on it is equal to 100, which is 150 minus 50. So you can put this over here. And if you click on the speed, it will give you what is the speed of the trolley. Since the trolley is not moving in any direction, you can say it is equal to 0 meter per second. Okay, now let us say, for example, if I now return this, click on this return, and I have two people over here. Two people here and one here. And now what I do is I click on the go button here. Now what's happening? So this force is higher, okay, and as compared to this, so the trolley moves this direction. And what is the speed? The speed is not going to be a constant, speed is going to change, which means the trolley is getting accelerated, right? So many concepts one can do, one can teach only by using this one here. If I want to keep it balanced, let us say, for example, I remove one of them here. I remove one of them over here. And you see, this is 50 Newton, this is 50 Newton, but still the trolley is not moving. Why is it not moving? Because the force is balanced. Now I can take this one and put it over here somewhere. Now this side is 150 and this is 50 over here. When I click on go, first I'll go to return. Okay, or maybe I'll pull this one also down over here. When I have something like this, will it move? It doesn't move. If I take this fellow and put it here, now you see, I just took it from here and kept it over here. Net force is 0, but still the trolley is moving. Why is it moving? Because there is no frictional force to stop him, and there is an inertia here. You see, so many concepts can be explained just by using simulations. Okay, you can ask the student to look into the simulation and then keep on asking the questions one by one. So this is how it's very helpful for us to just use a simulation and to start with the chapter. Okay, let us go on to the next one. There are other simulation tools here also. You have one for motion here. Okay, you can use this also here. Okay, so what you can do is you can make one person climb on top of it. So one of the excellent tools that I prefer. Okay, and I can now make this one apply a force. I apply a small amount of force. Now see, the robot actually leaves it and it now starts to move over here. Okay, what was the force applied? This was the force applied over here. I can give the values over here. I can make this fellow come again once again and apply a force. Now what is the force applied? 176 Newton. I've been applying for a long time. Now if I leave it, now what is the force applied on it? The same one. There's no force at all, right? There's no applied force. But still why the object is moving? Inertia, right? And if I want to click on the speed, then I will get to know what is the speed at which the trolley is now moving across. The trolley is moving at a speed of 14.1 meter per second. Now what I can do is maybe I can take this one, keep on top of this girl. She is holding this. Now as a result of it, now what's happening to the speed? Speed is not at all changing. Speed is remaining the same, right? Is there a new force acting? No, nothing is happening. You can click on the stopwatch also. How long will the person keep on moving? If I click on this timer, okay, the person has kept on moving as long as there is nothing been applied. There's nothing to oppose them. So as a result of it, you can say, yeah, zero force is acting on either side and the object is moving in a zero inertia, so it keeps on moving over here. Okay, you can keep on adding the objects one by one like this. You can keep on adding over here, okay, and then find out what exactly happens and so on. Okay, what is the force? Is there a change in the speed? You can look at all these things. This is how it is very helpful. You can ask n number of questions using this. This is how it is very. Let me move on to the third simulation. Now this simulation once again uses the same, this is not simulation, it's about the different questions, okay, which are obtained as a worksheet. Okay, this one also, I'll just put this URL over here, okay, in the video. You can look into it, you can download it, you can go visit this link, download, you can give this as an FA to students and ask them to work on it. Okay, so this will also be very helpful for you, right? Okay, so many questions, 31 questions. You think 31 questions will be attempted by your students? No. Okay, part of it you can make it as 2 FAs, or maybe you can divide them into groups and then you can do peer learning out of it. So like this. So simulations are one such great tool which I am always fascinated with. Okay, so given any exercise to teach with, you start with simulation, you will be able to be very successful in teaching that particular thing. But if you ask how do you make the students to get more marks, simulation may not be helpful in that case. So only way to make the students work is they had to work with the past papers. They have to come out with their own doubts. Okay, and without looking into solution, they need to look into it. They need to work on it. Okay, next. This is about understanding about the normal force. Okay, so what is a normal force? Will the normal force increase, decrease? You want to answer all of these questions. This is really a wonderful simulation. Okay, so now when I was just searching for it, I got this one. So very good one. What I can do is, let us say for example, an object is kept over here at rest. There's an mg force acting, there's an Fn force acting here, normal force acting over here. Okay, and then, so this is 10 newtons and minus 10 newtons, the slider can be changed. Weight of the box is 10 Newton, so therefore no other force is acted. So it's only 10 Newton, which is the weight, and there is only 10 Newton, which is the applied force. And what I will do is, I will now change this weight. Now what's happened? The normal force also, the arrow also increases in size, which means what? The mg and the Fn force are increasing over here. Now when I click on applied force, now this is only due to the weight. Okay, now the applied force here is 0. Now if I apply a force over here, now I apply a force here plus 10 Newton. What is it I am doing? I am now applying a force. Okay, I am increasing the force like this. And what's happening to normal force? Normal force is now decreasing. Which direction I am applying the force? I am applying the force upwards, right? So therefore, the total applied force would be normal plus the F applied should be equal to mg, right? So therefore, normal force equal to mg minus F applied. So as a result of it, it keeps on reducing over here. So you can very clearly say, okay, what happens to normal force? Will the normal force be always equal to mg, or will it be less than mg? Will it be higher than mg? You can make normal force to be higher than mg also. For example, if I apply a force in the negative direction, which means what? I have an object, okay, I have an object like this. I have an object kept on my mobile, is for example, my palm, and I apply a force on top of it. Now what's happening? As I apply a force, the normal force becomes larger and larger. As you can see there, normal force is becoming larger over here. So these kinds of things can also be explained to them by making use of the simulations. Okay, let me move on to that. Now this simulation shows you something like an object which is kept on a floor or on a table, and you have an you can push this across and you can monitor what's happening to the velocity versus time graph, VT graph, right? So the mass of the object is 1 kg, applied force is 10 Newton. Okay, there's a force that we will be applying over here, and then when I push it across. Now what am I doing here? Is the force being constantly applied, or is the force just applied for a moment and left it? The force is constantly applied. How do you know constantly applied? The reason is because, look at this diagram once again. See, there's an hand which is on top of it. There's a contact over there, right? So the contact tells you, okay, there's an applied force. So when there is no contact, then what can happen? We can ask these kinds of questions. How does the graph change? If I change the mass, for example, if I change the mass to, let us say I increase it to 5 times, then what happens to the graph? When I do it across here, you see the graph is now like this over here. Earlier, the graph was up like this, right? So therefore, the slope has reduced, right? So what does this indicate? What does it indicate? Acceleration, deceleration? So what is happening over here? So why does this happen? What is the equation governing it? You can ask n number of questions. Okay, move on to the next simulation. Now this simulation, which is from Java Labs, and this shows you, okay, so there are two, what you call rulers being given here. Let me reset it first. Where do we reset? Reset is here. Okay, let me reset it here. We have a 2 spring balances over here, which is one is connected to a 3 Newton, other one is 3 kg, another one is 1 kg. In fact, I can change any one of them. This is just for comparison, for looking at the Newton's laws. So there's a slider here which can be helpful for me to change this. There's the applied force over here. See, as I increase, the applied force keeps on increasing, right? So what I will do is I will keep it at 2 Newton over here. Both of them I keep it at 2 Newton, and one of them, the mass over here, the upper mass is for 3 kg, the lower mass is for 1 kg. Okay, and when I start this, now what do we observe? When I start the simulation, I observe the mass here is higher, okay, and it goes slower. But the 1 kg one, okay, with the same force, it has gone faster. And then you see, what about the arrows over here? See, the arrows here are very closely spaced, and the arrows here are very largely spaced. Okay, and here also same thing is happening. Now, why is this close and large space? What is happening over here? That means the distance is covered by this object. The 1 kg object is larger as we keep on moving farther and farther. That means as the time elapses, the distance is larger. That means it is getting accelerated, right? So you can find out what is the acceleration. So you can give this graph and ask them, okay, so the time is also given. What is the time? How do I know the time? So you see each arrow is spaced at a time interval of 0.1 second. And we can say, what is the distance covered, okay, between this point and this point, between this point and this point, with a view, calculate it using the formula and not with the scale. Then verify it whether your answer with the scale and this one is correct or incorrect, right? And maybe you can ask them to find out what is the acceleration. So you can do many things using this, right? And then, okay, sorry, you will not be able to calculate the distance. You'll be able to calculate the accelerations. I'm sorry, I made a mistake over there. Okay, you can find out the acceleration here. You can find out the acceleration here. Next, let us move on. There are many tools over here. As we keep on looking into it, we'll look into all these tools also, right? This one from Amrita Labs, it's one of the wonderful tools. So wherein you have a cart and you have a pulley over here, which is being fastened to, a pulley and a mass over here. It's a string over here, and it is assumed that there is no rotation or the pulley has a mass. What I will do is, I will make this bigger. Okay, now I have this one here. Now as a result of it, I can change the mass, I can change the parameters given here. I can change the cart weight, okay, which is initially 10 grams. I can change the pointer position also, okay, which is a reference point. Now what I will do is I'll keep this cart weight, change the cart weight to something like around 30 grams, or maybe I'll start with a higher value. I'll start with 90 grams, 100 grams. I'll start with 100 grams. So this is much more massive over here, okay, and then when I start this, let me click on this start over here, and I'll click on show results also. Okay, now what's happening over here? The acceleration seems to be 0.078. There's a pointer over here which shows what's happening. Okay, and how is the cart moving? The cart is moving slowly, and you can see the graph over here, distance versus time. It's showing a non-linear increase. Okay, so this is what you can see. It takes a very long time to start from that pointer position to reach over here. Okay, now maybe I can stop over here. Let me just find out what is the time taken. The time taken to stop at the pointer there is it seems to be 5 minutes and 8 seconds. This is what has been shown. Now what I will do is, sorry, not 5 minutes, 5 seconds and 8 milliseconds. Okay, let me reset this, reset the whole thing. And now let me reduce the weight. How much did we use? 100 milligrams we use, right? Let me reset it and keep it at 50. And then start this. Now what should you observe? You should observe that this cart should move faster as compared to that. So you should not take 5 seconds. It should be much faster to start from here and to reach here. Probably it can reach maybe within 3 seconds, right? Is it reaching the 3 seconds? No, just cross 3 seconds also. But anyway, at 3 seconds and 40 milliseconds. Now we should ask the question. See, I have reduced the weight mass, weight 50% of it. Okay, and I observe the time is not exactly half of it. Now, why is it like this? Okay, we can ask these kinds of questions. How is the time related to this, right? So these kinds of questions can be asked. And from the graph, can we infer anything? Or the student should come out of it, okay? They should be able to say it's not a non-linear relationship to get that kind of result. It's a non-linear one, so you might not get the result, right? So this is very helpful for them. If they are able to answer such kinds of questions, they can easily do their IA, EE, okay, their evaluation part, and as well as they can do well in the paper 1B also in IB. Okay, now let me move on to the next one. So you can do multiple experiments using this, right? You will be able to find out the free body diagram. You can find out what is the tension here. You will be able to find out what is the acceleration of the particle. You can do many things. You can ask them to do it, right? Next one is this we have done. Very similar thing over here. You can actually put the friction also here. In addition to this one there, you can also put a friction. I think The previous one also we had a friction there, right? Let me just find out. Did we have a friction here? We didn't have a friction here. Okay. Let me, if I maximize this, I'll get to know. No, there was no friction here. Okay, only here you have a friction, right? So you can put the friction here and then repeat the same experiment and ask them how does it work. Let me just reset this. Okay, so you have this one here. Okay, there's a pulley and it's been made to move down, and I can put this coefficient of friction to be 0.2, for example, and then I can start this. It says too much friction, which means what? The object is unable to move, right? Now, therefore, now what I should do is maybe I should increase this value. Let me increase this to 5 grams. So reset this and make this as 5 grams over here. And then you can ask, okay, for what value of the mass that I have added will the object starts moving, right? See, here also too much friction over here. That means I asked them first to calculate it based on the math they are able to solve it using the free body diagram, and then ask them to substitute that math and finally get the answer. Okay, you can do this one also here. Okay, so therefore, now I can reset this. Maybe see by trial and error, see how many times I'm doing. I'll make it 15 grams over here. Now, again, too much friction. The object is not able to move at all, right? It's still there itself. Now, let me restart this. Let me make it as around 50 grams and see whether it is able to move. Wow, it's able to move. Now I can ask the question, hey, what is the minimum weight that I need to add so the object is able to move? Do 1 or 2 trials in the classroom and show them, okay, this is what I'm doing. And at the end, you can say, okay, this is what I'm doing. And as a result of it, you need to figure it out. Okay, what is the minimum weight that I need to add? So it just begins to move. And based on it, you can say, okay, what is the kinetic friction coefficient? What is the sliding? What is the limiting friction coefficient? You can ask all these questions over there, right? And how does the graph change when the friction is 0, when the friction is more than 0? Okay, so you can ask these kinds of questions also. Okay, it is like we ourselves are framing a new structured question based on this. Okay, this actually gives us that kind of ability to do all these things. That's how way the simulations are very useful. Okay, let me move on to now this one. This many of you could relate. You could, if you have the Vernier Pro in your lab, okay, you would have done 1 or 2 experiments based on this. We restart this. So these are the 2 photo gates that we have, and then there is a cart which has been given over here, and this cart can easily slide onto it, and then you can see. Let me reset this. Okay, you can see that this has a cardboard of length 21.6 centimeter, and now this should passes through it. As this passes, the moment initially what happens is there is a infrared ray which is passing through this one, and the moment it cuts it, okay, it records the state 1, the time at which it cuts, and then first end, second end, it cuts it out. And similarly, when it cuts the second photo gate, also it finds out, and then the distance between them is measured, the time between this is measured, and finally you can calculate the average velocity or whatever you want, right? Now you can increase the mass over here. You can increase the mass. I can increase to 100 grams, for example, and this also I can increase. I can make it to, this is the maximum. I think I can only decrease this. Okay, I can only increase it to 4,000 grams. That's it. 4 kg is the maximum over here. And then I'll return. And then what I can do is I can click on the start. Okay, so which means it records the values over here in the table. And then I can click on the start button. You see, it is going slowly because this was 4 kgs and this is only something like 100 grams. So it moves slowly. The first state records to 6.301, second 6.8892. Here, similarly, it records all this value, right? Once it is done, we have got this value, then you take the difference between these two, and therefore you find out what is the time taken, and you can find out what is the average velocity, right? So this is how it will be useful, and then you can relate it to tension, you can do all these things. I was thinking whether, okay, if someone can do something like changing this distance between them and finding out whether the acceleration is constant, average velocity is constant. You can do many things like this, right? Or you can ask the questions based on this. Next simulation. Now, we have seen so much amount of simulations. Now, this is your, what you call the quiz. Okay, so now in the quiz, now what has been given here, right? Force is applied to a dresser to accelerate it to the right across the bedroom floor. Ignore air resistance. There's a object kept over here. You can now apply the rightward force. Rightward force is applied, and then identify the type of forces in the relative magnitudes, tap a direction, similar to that of what we had seen in the earlier. Like for example, in graphs also we have the same thing, right? So this particular site gives you what you call quizzes in this way. You can also use this one here. So you can say, is the right selected direction right? Okay, and then you can say applied, F applied. Okay, which is the right answer? You can click on this, tap an arrow on the diagram to change the size of the force. Tap check answer when ready. Okay, so now selected direction is a ID the right word force. Okay, which is the right word force? Is this the right one? Now you have none. Gravity we have done. Sorry, upright we have done. Gravity, is it the F gravity acting here? Is air resistance acting here? Is normal acting here? Spring force acting here? Friction acting here? Tension acting here? What is being acting? Okay. So how is it done? A right force applied to a dresser to accelerate to the right across the bedroom floor. So therefore, what I can say is I can say maybe F applied is here. You can check on this answer. And if it is right, if you get the correct answer, if it is wrong, then definitely it says your FBD has errors, right? So therefore, so you can rectify this, you can get to know how to solve this one here. So this is how, okay, you'll be able to solve questions, and really it's a wonderful tool to understand the kinematics part of it, or mechanics part. Let me move on to the next one. This one is a bit complex. Okay, so one of the best tools I have seen so far, Quizlet, and I have not been paid anything to recommend this, but really a wonderful tool. So what it does is, okay, frame by frame or question by question, you have an animation. That's a wonder of this. Now what I'll do is, let me start with this one here. It says, okay, so Newton's first law. Let me click on the first animation, play this. Now it shows you something like this. A ball is being thrown from here, it comes down. Now you can ask the question, the dots are not equispaced, dots are being farther spaced. Why is this happening? Okay, acceleration due to gravity. And you can click on the second animation. Click on this. Now you see that this is showing a projectile motion here. Now when it is showing a projectile motion, okay, now can we apply the laws of projectile motion over here? First, and secondly, why does the object once again come back and fall onto the puck? You can ask this question here. And then you can also ask, see, the distances here is also not uniform. It is being putting over here. It is being showing like this over here. Is it once again due to acceleration due to gravity? And if so, now why is it showing only along the y-axis? Why not along the x-axis? Right? You can put that also. Or maybe you can still ask, if suppose if I map these points along the x-axis, okay, will I also get a similar pattern where the distances are farther or distances are equal, or what can I get? So many questions can be asked. So it actually gives us an overview of what all kind of questions we can ask. That's how it has been useful. And then you can have, there are several examples over here. You can draw the free body diagrams over here. When I click on this, okay, so for example here, okay, let me click on this free body 1x. So when I do this, what is the free body diagram? So you see normal and mg are acting over here, but okay, only f is being shown over here, right? If I take the second one, now what's happening? What is happening over here? You can ask them. Okay, so something like an upward force, sideways force, right force, and a left force is acting. What is that left force? Maybe air resistance, maybe friction. You can argue based on, you can put across your comments based on this, right? So this is how it is very much useful over here. Mass and an incline, for example. See, what I can do is, just a moment, I can click on this. Okay, so before that, let me reset this just a moment. Check, then reset value. I have this value and click on this. Now you see it gives you what is the speed value, when the speed increase, decrease. You can get to know more about this, right? Okay, so now let me move on to the next one. So you have explorations over here. Okay, you can click on each one of them, try to answer them. You can ask them to answer. You can give them problems which are free body problems or whatever it is. You can ask them to work on it. Okay, really a visual treat, I can say. Okay, for those who are interested in solving problems. Wonderful one. The next is a gamified one. I will not be able to show you this one because I don't have an iPad. But those who have an iPad, you can just direct this one, download this one, and you can try working it out. And if possible, you can also do this one and send me a video so I can upload it to my site. For others, okay, who have not seen this, this was so useful. It's something like an astronaut trying to grab something, okay, and then space trying to grab something, okay, and Newton's third law, how does it obey, and so on. So nicely it's been done, it seems. I have not seen this, but anyway, if you get it across, do put it across. Finally, the last one, Newton's third law of motion, which is one of my favorite one. You can use the simulator to do it, or maybe you can also look at the You can also look at the video. That's how does it work. Okay, so what is shown over here is nothing but you have two spring balances over here, and you are going to apply a force over here. See, it's already reset. Apply a force. When I apply a force, you see here also it is 100, 150 here also 150. I do one thing, I start from the beginning. See, both the pointers are showing 0 over here. If I apply a force of some value here, now what do you observe? Here also it's 100, here also it's 100. Okay, both of them are showing 100 and 100. Why is it so? Okay, you can say if one of them is action, the other one is reaction. So you can actually give this to students, and then you'll be able to, the student should be able to come out with the answer for this. So this is what one can do with this. So thus we have seen around 10 to 11 tools based on Newton's laws of motion and how to apply free body diagram. If you find it interesting, do share, like, and subscribe to my channel. And also let me know what best works for you and what are the good practices, best practices that one can do with it. So it will be helpful for me also. So I can also share with my fellow colleagues who work with me. So to suggest, okay, what best we can do to make the learning more enhancing or more effective. Thank you. Thank you once again for being with me. See you in the next video.